Hey guys, in this video we are going to discuss the limit of a sequence. Suppose we have a sequence which is given here is so this is the general term. So this represents a sequence like this. A is up. Wait a second. So something like this. A list of numbers. A is up 1, A is up 2, A is up 3. Dot, 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 dot. This is the general term A is up n. So we have an infinite sequence, right? Infinite sequence like this. As n tends to infinity, what happened to this sequence? As n tends to infinity, the index tends to infinity. This index 1, this index here tends to infinity. The list of numbers, this list of numbers approach a number called L. So this is called the limit of this sequence, right? So we try to understand this one graphically, and we try to understand the definition of that. So this is the definition. So for every epsilon, positive epsilon, we can find an integer n with this property. Yeah, so in this video we are going to understand this definition as well as this one here. So what does this mean, right? What does this mean? All right, as I said in my previous video, we know that a sequence is a function of indices. So this is the indices. The first index is 1, first term. The second index is 2, 3, 4, 5, 6 up to infinity, right? So the first term, the first index maps to this value here, A sub n, say A sub n. The second index maps to this value, which is a -1, and third one maps to this, like that. Nth one maps to this one. So as I said before, so keep that in mind, right? A sequence is a function of indices. It is a real function of indices. These are the indices. So this is the first index, second index, third index, and so on, right? So this is called first term, second term, third term, fourth term, and this is the general term, nth term, right? All right. So when you look at this sequence seems to be converging to some now value here, right? You look at this sequence seems to be converging to some number here. Let's draw that. Oh yes, that, let's say that value, that number is capital L, uppercase L, right? This is the number. This one seems approaching this number as n tends to infinity, right? All right. So we denote that. So this, your sequence A sub n approaches the number L as n tends to infinity, right? As your index tends to infinity, these terms converges. This term, this sequence converges to this value L, right? So how do you see this one in another way? How do you write this one in another way? In another way, mathematically. How do you write this one in a mathematical way? So, here, so this is the value. This is the so this sequence converges to this value L. So if you take any positive epsilon, let's consider any positive epsilon. That. All right. Let's consider epsilon is a positive number. So I consider a strip, a ribbon around L, right? So this is the ribbon. So the width of this ribbon, this side is epsilon, this side also epsilon. So the width of this ribbon is 2 epsilon, right? 2 epsilon, right? Then what can I say? So what I can say is, so I can find an integer index here. Look at this. So this number is outside of this ribbon, and this number also is outside of this ribbon. But after this, here let's after this one, this is let's take this one is fifth one. So this one is the fifth one. This this point also, this number also, this numbers also seems to be outside of this ribbon, right? But after this index here, right, after this index, all points of the sequence are within this ribbon, right? That means I can choose an index. This index depends on this epsilon value. So if your width of this ribbon around L is very large, say, let's draw another one. Let's use this color. So let's say if you choose a ribbon, so a ribbon around L, epsilon, and I have to write this. It's epsilon. This one also epsilon. So if you choose another epsilon, say this is epsilon dash, right? Around L, then what can you say? So you so this one is within this band, this ribbon, the ribbon of this one, right? Within this bigger ribbon, and this one outside. This one is located outside of this ribbon. But after I can say after this index, this time for this epsilon, right? After this index, all terms of the sequence are inside of this ribbon, bigger ribbon. So definitely this number here depends on epsilon, right? If the sequence say let's consider another sequence which is not convergent, right? So let's consider this one. This is an alternative sequence. Plus 1 minus 1. The first term is plus 1. This is the first term is plus 1, and the second term is alternative sequence negative 1, and third term is positive 1, fourth term negative 1, positive 1, negative 1, positive 1, alternative sequence, right? So if you consider this sequence, you cannot find a number. There is no this. First of all, I want to mention that this sequence does not converge to a number because it is alternating between positive 1 and negative 1. If you assume this sequence is convergent, right? Around convergent, this sequence converges to 1, let's say like that, right? Let's assume that this sequence converges to this number here, 1. This is also 1. If you choose epsilon something like 1/2 around this number, so definitely, so this gap is the width of this ribbon is 1/2, and this width also 1/2, right? 1/2. Then this now what is the value of this? This is 1/2. This is 3 1/2s. 3 1/2s, right? So what happened? Can you find n naught? Can you find n naught so that all terms after n naught lie in this ribbon? No, right? You cannot find n naught because so if one term is 1, the next term is negative 1. It is outside of this ribbon. So this sequence is does not converge. So right, let's go to our previous one. So this is a convergence sequence. So we try to understand that definition of limit, right? So let me show that definition. So this is the definition of this limit, this one, right? Alright, I'm trying to explain this one. Right? So for every epsilon there exists an integer such that all integers bigger than this number implies, so this means, so if you write this one, so if you expand this one here, you get this something like this. So this is your ribbon. Yeah, this is your ribbon. So this is your ribbon, right? So let's read this one again. For all epsilon there exists an integer capital N such that all integers bigger than this n, uppercase N, implies the terms of the sequence within that ribbon after this index, after n or n, capital N, uppercase N, after uppercase N, all terms after uppercase N lie in this ribbon. This is the ribbon here. L plus epsilon. So this is your L. This is your L plus epsilon. L plus epsilon. This one is the L minus epsilon. This is your ribbon. So terms of sequence after this number, the terms after this number within this ribbon here, this ribbon. So this is the definition. This is the definition of limit of sequence, right? Here I found a nice picture for you. So A sub n is a sequence, right? So this is the first term, second term, third term, fourth term, fifth, and so on, right? So this is your ribbon, the ribbon around L. This sequence seems to be converging to L, right? So now I draw a ribbon around L. So the width of that ribbon is 2 epsilon, right? So this gap is 2 epsilon. This gap is 2 epsilon, and this gap is epsilon, and this one lower one also epsilon here. Epsilon. If you place a ribbon around L, you can grab if it is convergent. If it is convergent to this number L, right? If you put any ribbon around that, you can pick an index, right? After this index, you can say all terms of the sequence lie in this ribbon. Then you can say that limit this the limit of this sequence is equal to this number L, right? So definitely the this index n here, capital uppercase N, depends on the width of this epsilon, right? So if you place a ribbon around L, some yeah, if you place a ribbon like this, then our the capital N would be a different value, because this capital N depends on this epsilon, right? So we got 4. So right, so I hope you understood this one here, the graphical representation. So if you have a convergence sequence like this, then if you take any epsilon, positive epsilon, right? If you consider any positive epsilon, you can grab an index, uppercase N, capital N, so that after that index, the all terms after that index, see, all terms after that index are within that ribbon. Then you can see that sequence converges to this number L, right? I hope you understood that definition, right? Let's write that down. So let's write that down. For any epsilon, if you select where is it? So if you consider, so this means for any epsilon, positive epsilon, you can find an integer capital N or N naught, such that all terms after that index, you can say like that. So this is an index of your sequence. All terms all terms after that index are in that ribbon. This should be negative, yeah. L minus epsilon, L plus epsilon. This one is same with this. A sub n minus L less than epsilon. All terms after this index are within this ribbon, That ribbon, the width of ribbon can be any number, right? The width of ribbon can be any positive number. If you pick any positive number, you can grab this one here. You can grab this index such that all terms after that index are within this ribbon. That's the definition of the limit. So this is the definition of I hope you understood the definition very well, right? So let's, in my next video, I'm going to work out a small question or small problem. So how do we use this definition to show that a sequence converges to a number, some number? So let's do that.